Z-scores give us a way to determine if a data value is far from what we might expect or closer to a typical value. For example, we might like to know if a fruit tree is producing a significantly high number of apples, or is my son's height typical for a 5-year-old? Before we calculate a Z-score, let's first look at some notation. In statistics, there are different pieces of notation for populations and samples. Remember that a population considers all subjects, whereas a sample is a subset of that population. So it is likely, for example, that the mean of the population is not going to be exactly equal to the mean of any given sample. The mean for a population is represented by the Greek letter mu, and the standard deviation for a population is represented by the Greek letter sigma. The mean for a sample is written by x bar, and the standard deviation for a sample is lowercase s. Let's suppose that the entire population has a mean IQ score of about 100 points, with a standard deviation of 15 points. Then we could construct a normal distribution that looks like this, starting with the mean value of 100 in the center of the distribution and adding the standard deviation of 15 to come up with our interval along the horizontal axis. Now let's introduce z-scores. A z-score is the number of standard deviations a data value lies away from the mean. So even though the standard deviation is 15 points, we know that the value of 115 is one standard deviation above the mean of 100. So the z-score for 115 would be 1. The z-score for 130 would be 2, because 130 is 2 standard deviations above the mean. The z-score for 145 would be 3, because 145 is 3 standard deviations above the mean. The mean value of 100 will have a standard deviation of 0, and the value of 85, although it lies 1 standard deviation from the mean, due to the fact that 85 is less than the mean of 100, our z-score will be -1. 70 will have a z-score of -2 because 70 lies 2 standard deviations below the mean, and 55 would have a z-score of -3 because 55 lies 3 standard deviations below the mean. I have only labeled z-scores, which are integers in this case, but z-scores can be any real number. For example, there is a value between 130 and 145 that has a z-score of 2.71. Let's summarize some key properties of z-scores. The mean value of a data set always has a z-score of 0. Data values less than the mean have negative z-scores, while data values greater than the mean have positive z-scores. A data value is considered significantly high if its z-score is greater than or equal to 2, and a data value is considered significantly low if its z-score is less than or equal to -2. Back to our example with IQ scores, any IQ score that is greater than or equal to 130 would be considered significantly high, and any data value that is less than or equal to 70 would be considered significantly low. Let's calculate the z-score for an IQ score of 123. Because I have this normal distribution drawn out to look at, I can determine that the z-score for 123 will be positive because it is larger than the mean, and I can also determine that my z-score will be somewhere between 1 and 2 because 123 falls within the first and second standard deviation from the mean. To find the z-score for 123, we take 123 and subtract the mean value. This will tell us how far we are from the mean. But then we need to divide by the standard deviation of 15. And now this will tell us exactly how many standard deviations this data value lies from the mean. This z-score is approximately 1.53. Please round z-scores to 2 decimal places. Now let's find the z-score for 66. To find the z-score for 66, we would subtract 66 minus 100 and then divide by 15. The z-score is approximately -2.27. Looking back at the distribution, we can see that our answer makes sense because we are a little over 2 standard deviations below the mean, and that is why we have the negative sign on our z-score. We could also say that someone with an IQ score of 66 would have a significantly low IQ score because their z-score is less than or equal to -2. To find a z-score using the population mean and population standard deviation, we use the formula z equals x minus mu all divided by sigma, where x is the data value of interest. To find a z-score using sample data, we use the formula z equals x minus x bar all divided by s, where again x is the data value of interest.